So today's class is meant to fill a gap in the tree's foundation videos. So for example, when we are, let's say, searching for, say, 13, then we start by looking at the root and comparing 13 to 15. So since 13 is less than 15, we can decrease the problem now by going down the left subtree. So in one comparison, we have reduced the problem size, we've decreased the problem size by at least 4 elements here. And since 13 is more than 6, we go down this path. 13 is more than 7, so we go down this path. And there we find 13. If we were looking for, say, 12, then 12 would have been less than 13, so we would have gone down this path. 12 is more than 9, so we would have tried to go down, follow the right pointer here, but since it's null, we would have detected that 12 does not exist. And so the path that we are following when implementing search is basically a path whose length is, in the worst case, proportional to the height of the tree. And we did a similar thing with insert. So suppose we are given a binary search tree and we are trying to insert 13. So just ignore the fact that 13 is already there. Let's assume it's not there. Then we first do a search. So we start from the root. 13 is more than 12, so we go down this path. 13 is less than 18, so we go down this path. 13 is less than 15, so we try to go down this path, and that's where we stop because we know 13 isn't there. We're going to assume today that all the um, elements are distinct, and that's because these elements are going to be assumed to be key value pairs, which means for every key value pair, there should be a unique key. The values might be associated attributes which are stored alongside the key, but the key has to be unique. Um, Otherwise, we can't really use this dynamically changing collection as a dictionary or as a map. So 13, because it's not there, we know we have converged on the place where it should have existed if it was in the tree, and so that is the point where we insert the node 13. So we always insert a new node as a leaf in the binary search tree. That's what we did in the foundations. And then for delete, we had actually 3 different cases. So suppose after inserting 13, I want to delete it, then I would again do a search for it in the tree, and then once I find it, I see that it's a leaf node, and so I would just remove the pointer to 13 from its parent. So when it came to delete, the simplest case was uh, when the node that we are trying to delete, let's say X, is a leaf node. That was the most straightforward case. Case 2 was where X is an internal node, which means it has children, and uh, a simpler case is when it has only one child. So in this diagram here on the left, so I've picked these figures from Corman's algorithms book. So let's say we are trying to delete Z, and we followed a path down from the root. Let's say Q was the immediate parent of Z, and we finally found Z. And the left pointer points to null. It has a right child, it has a single right child. And so in that case, what we did is we just redirected the pointer from the parent of Z to Z to now point to directly to to the child, whatever that child is, R. And by doing so, we removed Z from the tree. And asymmetric cases where Z does not have a right child. It has a single child, but that single child is a left child. So in that case, we would redirect the pointer from the parent of Z to Z to now point to L, bypassing Z. And so that would effectively remove Z from the tree. So these are the two resulting structures we get when what we are removing has only one child. The most complex case was when the node that we were trying to remove has two children. And when it has two children, let's say we want to remove this particular Z here, notice that it has a left child as well as a right child. And so now we had to figure out a way to remove it so that the search property, the binary search property, is not violated. So the search property in a binary search tree is that every node that is less than Z should be in the left subtree of Z, and every node that is bigger than Z has to be in the right subtree of Z. So to make sure the property is not violated, we either picked the predecessor of Z or the successor of Z, one of the two. So in this case, let's say we are picking the successor of Z. We search for the successor of Z, the in-order successor, and we take the value and we transplant it, or we copy it into Z, the node that contains Z. So effectively we are overwriting Z with the value of its immediate successor, and by doing so we can now physically delete the successor from the tree. We don't physically delete the node that has two children, but we go down to its successor. Since the successor is obtained by taking one step to the right, following one pointer down this subtree, and then finding the smallest element in this subtree by successively following the left left pointers from the root of that subtree. And so whatever node we end up at, that node is not going to have a left child. So in this case, the successor of Z is, the in-order successor of Z is Y itself, and this Y will definitely not have, in this case it doesn't have a left child. So what we do is we take the value Y, we copy it into this node Z. So Y comes here, and then we physically pluck out this node Y, similar to case 2, by bypassing the pointer from Z, or basically we remove this pointer and make it redirect here. And so the resulting structure would be this. And in the general case also, where the successor of Z is obtained by taking one step to the right and then following some path down a sequence of left pointers until we reach a leaf node that has no, whose left pointer is null. This is the successor, the in-order successor of Z. So we copy this value Y into uh, into this node Z. That's what we do here. And then we have to physically pluck out this node. How do we physically pluck out this node? Well, we'll take whatever the parent of that node was, and we reorient the pointer from the parent to that node to point to whatever the single child of that node is. If at all it has a single child, maybe the in-order successor of Z does not have any children, but it will definitely not have a left child, because we follow all the left pointers as far as we can down this subtree. And so by we pluck out this node exactly like we do in case 2, and by doing so we preserve the binary search tree property, as well as it becomes relatively easier to implement this deletion. So the resulting structure is something you can see here. Y has moved into the physical node that contained Z earlier. Z has disappeared, and uh, the node that corresponded to Y has been plugged out. So you don't see that in this sequence. Now, all of these operations, as you note, insert, delete, and search, they they take no more than uh, order of the height of the tree in terms of their time complexity, because we just go down the tree once, and even if we find uh, the node to be deleted somewhere in the middle, to find the successor we would keep going down one of the subtrees of that node. And so in the worst case we will at most follow a path whose length is the height of the tree. So the problem is that if we build up this dynamically changing collection that we talked about by sequentially inserting nodes in ascending order, so we have no control over what order these values are going to come in. And so if we go with this particular way of implementing things that we discussed in the foundations, then when we see one first, we will have a one element tree, and then when 2 comes in, we will have to make 2 the right child of 1, because that's where 2 is supposed to go. Then when 3 comes in, we search for where 3 should go. It should go here, so that's where we end up inserting it. And so we end up with a linear chain whether the numbers come in sorted order or even if they come in reverse sorted order, the chain would just be pointing to the left. But the height of the tree in such cases is not order log n, it's order n. And so when we talk about the dictionary operations insert, delete, and search, which implement the dictionary abstract data type, they would all take time that's proportional to n. And so this is not efficient. We know that real libraries that implement maps as trees are not going to be using this particular implementations.
Want to become a software engineer at Google? You can, like thousands of our students. You just need to learn from those who've already cleared FANG interviews. At Interview Kickstart, our interview prep courses are developed and taught live by 150 plus instructors from Tier 1 companies like Google and Facebook. Our courses are tailored to help you crack software engineering domain interviews, including back-end, full stack, machine learning, embedded systems, data science, and more. To learn more, book your free webinar slot today